Hello, and welcome to the video on chemical safety in material science and engineering labs for the Department of Material Science and Engineering at Johns Hopkins University. The purpose of this video is to provide a basic introduction to principles of working safely with chemicals in the laboratory. It's a relatively short video, and so we won't be able to provide all of the details necessary for working with particular chemicals in your specific lab. However, we hope to provide enough general information that the broad principles that you learn you'll be able to apply to your specific situation. I'd encourage you to talk to your principal investigator, that is your research advisor, or other members of your research group for specific information with regard to your particular laboratory. By way of motivation, let me start with an example, a very unfortunate case study in what can go wrong in an academic lab. This is Sherry Sanji. She was a research scientist at UCLA. She had fairly recently graduated with her BS degree in chemistry, but she had a couple of years of work experience. So she was a fairly experienced chemist by the time she started her research scientist position at UCLA. In the work that she was doing there, she worked with pyrophoric chemicals, in particular tert-butyl-lithium. Pyrophoric chemicals, if you don't remember, are chemicals that combust spontaneously when exposed to the oxygen in the air. So when we work with these chemicals, we invariably do it using sealed containers, usually under an inert gas, and we take great care when handling the chemicals to make sure that they are never exposed to air. Unfortunately for Sherry, in the particular day that she had her accident, something really went wrong. She was trying to transfer the pyrophoric chemical from one container to another using a syringe, but the plunger of the syringe came out. About 50 milliliters of tert-butyl-lithium were exposed to air and caught fire. This, of course, was a serious accident in its own right, but it was made worse by the fact that in the fume hood was an open container of hexane, which was not part of the experiment, and in the course of the accident, Sherry apparently knocked over the container of hexane, which spilled and also caught fire. The hexane and tert-butyl-lithium, which were on fire, splashed onto her clothing, which also caught fire, and she received third-degree burns to much of her torso, to her neck, and also to her hands. And unfortunately, she died as a result of her injuries later in the week. One thing that in my mind makes this particular episode especially tragic, just beyond her death, is that if the training that she had received had been more effective, she probably would not have died. And this is true in a variety of regards. First, there's a question about how much training she got in dealing with the particular chemicals that she was working on. As I mentioned, she did have some experience in chemistry. She had a BS degree and she had some work experience. But it's not clear how much experience she had working with pyrophoric chemicals in particular. So there's an issue of the degree of training that she received. In addition, however, there were some particular failures that contributed to the severity of this accident. One is simply having the hexane in the fume hood, even though it wasn't part of the experiment that she was working on. It certainly made it worse. Even worse, however, was the fact that she was not using appropriate personal protective equipment in the form of a lab coat. As I mentioned, the chemical spilled onto her clothing, which caught fire. She was wearing a synthetic sweater, which is particularly flammable. If she had been wearing a lab coat, the chemical still would have caught fire, would have spilled on her lab coat, but having the lab coat on, which would be more resistant to burning, particularly a lab coat that had been treated with fire retardant chemicals, would very likely have given her the time that she needed to remove the lab coat and douse the flames, or at very least given her more time to extinguish the flames on her clothing before she herself was severely burned. So the accident was much worse than it needed to be for lack of proper personal protective equipment. Finally, the other person that was in the lab at the time, another postdoc, also, although he tried to help Sherry, was not particularly effective. in order to extinguish burning clothing, as children were usually taught the stop, drop, and roll technique. Alternatively, she could have gone to or been assisted to go to a safety shower, which would have doused her with enough water to put out the flames. Instead, the postdoc tried to help her by smothering the flames essentially by hand using a lab coat that was nearby. And when that didn't work, he resorted to dousing her with water that he was carrying from a nearby sink. And although he was ultimately able to put out all the flames, the injuries that Sherry sustained were so severe as to cause her death. So although incidents will sometimes happen in laboratories, although we try to minimize their frequency, the severity of incidents also reflects on the level of training and the extent to which people are following established procedures and taking the appropriate steps to protect themselves. So in using this to introduce this safety training video, what I want to drive home is that the things that we talk about, although the material may seem at times dry, the things that we talk about actually have real relevance for the things that go on in our laboratories. There are chemicals and equipment and procedures in our laboratories that have the potential to seriously injure or to kill us if we are not treating them with respect and following safe procedures. So with that as a lead-in, I strongly encourage you to pay careful attention to your training, both in this video but also in the specialized training that you receive in your lab, and to take it to heart, because the things that you learn here and in your other training could very well save your life or that of someone else. With that said, let me reiterate a couple points of basic philosophy on behalf of all of the faculty in the Department of Material Science and Engineering. First and foremost, we strongly believe that no experiment is so important that it should jeopardize the health or safety of any individual in our department or anyone else. The corollary of that is that safety is of the utmost importance in everything that we do. When we plan our experiments, when we conduct our work, we have safety first and foremost in our minds, and only when we are convinced that we can do things safely do we then move to more prosaic issues of actually getting the work done. Planning is an important part of this. Right? We don't undertake any experiment without some prudent consideration of the safety implications of that experiment. That isn't to say that every experiment, no matter how minor, needs a detailed safety review. Prudence involves deciding what the appropriate level of review is, even if it's only a mental checklist. But the idea is that the safety implications are thought about before we start the work. Our goal, of course, is to have no incidents at all. No incidents in which someone is injured, or not even any incidents in which there's a significant chance that someone could be seriously injured. What goes along with that is we also don't accept excuses. If there is an incident, we don't accept an excuse that says, well, we had this incident, but it happened because of X. Right? The idea is that we think ahead of time about the things that can happen. We try to even think about things that are unforeseen, and then we plan for them appropriately so that we have no incidents, and that if we do have any incidents, that the risk to the health and safety of everyone in the department is minimized. Now, this video will be approximately an hour long, and in an hour I can't possibly give you all the detailed information that you might need in your lab. So an important thing to do is to start out by pointing you to places where you can look for additional help. And one that I would particularly like to recommend to your attention is this book, Prudent Practices in the Laboratory, Handling and Disposing of Chemicals, produced by the National Research Council about 10 years ago. The reason I like this book is that it is very practical and very handy. It's not written with a bunch of jargon. It's not written with a bunch of legalese by people trying to cover themselves against any sort of liability. It's full of really practical advice that you as a graduate student or as a postdoc or as a principal investigator can put to work in your laboratory. And so it's very handy. In particular, in the back of this book are really down-to-earth, easy-to-read summaries of the hazardous properties of a wide variety of chemicals. It's not comprehensive, it couldn't possibly be, but it's very practical very handy, and I highly recommend it. And much of what I'll talk about in this video is actually drawn directly from this book. With regard to Johns Hopkins in particular, we have a Health, Safety, and Environment Office, which stands ready to help us with a wide variety of aspects of dealing with safety issues in our lab. In particular, what they do is they publish a set of policies on how to handle a wide variety of laboratory situations, how to deal with hazardous chemicals, how to deal with cryogenic fluids, how to deal with radioactive materials, and so on. So let me just point out that these things are available on the web at the safety website. You can search for policies on a variety of different things. Here I've just reproduced part of the first page of the one on, which is maybe most important for many of us, policy number 703 on management of hazardous chemicals. And only a little bit is shown here, but it's all sorts of guidelines on how to work, store, and dispose of chemicals safely. And on this website there are many more policies which you can refer to for more detailed information. And if you don't find a policy on the thing that you're looking for, you can certainly come to me as a safety officer of the department, or you can go to the safety office directly and ask them for guidance with what you want to do. I think I can speak for the people in the safety office when I say that we would all much rather have you come to us or come to the safety office and ask for advice on how to do something safely ahead of time, rather than have to respond to an incident where something happened that involved potential injury or even loss of life. So with that said, an outline for this particular course, the topics that we're going to cover would include prudent planning of experiments. Right? How do you plan an experiment properly without going overboard? Part of that is evaluating the hazards and risks of the things you're doing in the lab. We'll give you some guidelines for how to do that. We'll talk specifically about how to manage chemicals, including things like storing and transporting chemicals. We'll talk about how to work with chemicals, in particular how to use proper protective equipment. And then finally, very importantly, we'll talk about how to dispose of excess chemicals or chemical waste. Let's begin with planning. It may seem obvious, but the level of planning for an experiment that's going to be required will depend both on the details of the experiment, how much material are you using, how hazardous is it, but also on the experimenter. Someone who is, say, a graduate student or a postdoc who's been working with a particular class of chemicals for a long time might be able to plan a new experiment with just a simple mental checklist, whereas, say, a graduate student who is approaching the experiment for the very first time might need a little bit more formal planning in order to work safely with those same chemicals and procedures. So planning can take on a range of levels. As I said, for a straightforward experiment by somebody who's experienced, it might just be a simple mental checklist. What are the materials I'm working with? What are their hazards? What personal protective equipment do I need? What will I do if something goes wrong? At the next level of formality might be a discussion of the experiment. So even an experienced experimenter, if he or she is planning on doing something new or working with new reagents, might talk with other people in the lab or with the principal investigator about the risks and hazards and how they can be minimized. For things that have the potential to be very hazardous, there is a formal hazard review process that involves the safety office. So for example, in Professor Katz's lab, not too long ago, they wanted to start working with small quantities of explosive materials, things like TNT. And so they actually involved the safety office in that process to get a very thorough safety review before they started working with those materials. The steps in planning an experiment might seem fairly obvious, but let's just lay them out here very quickly. First of all, we want to be able to evaluate the potential hazards associated with the materials, the chemicals, the processes, and equipment that we're going to be used. If you're contemplating using things that are especially hazardous, you might want to consider alternatives to those chemicals or those processes. And this is where talking with somebody who's more experienced can often be a big help. Those people can often suggest alternatives. We need to think about how the chemicals that we're going to use will be acquired and how they'll be stored. So as a trivial example, if your lab has never worked with flammable chemicals, you'll need a flammable chemical storage cabinet in order to store things. We think through the experimental procedure and then identify any necessary protective measures. Right? Do we need to work with these chemicals in a fume hood? What personal protective equipment is required? And so on. Finally, we think about the waste that will be generated and how we'll dispose of it. If we know the character of the waste, we'll know the hazards that may be associated with it, and that will dictate how it can be disposed of. And again, we'll consider alternatives in order to minimize the amount of waste that we generate. Generating waste creates potential hazards and also creates expenses in disposing of the waste. Let's move on now to talking about how we evaluate hazards and we assess risks in the lab. Again, we won't be able to cover all the hazards and risks that you might face in any sort of detail, so let me begin by pointing out sources of information. We start with the thing known as an MSDS, or Material Data Safety Sheet. Material Safety Data Sheet, sorry, this is in the wrong order here. These are available on the web. You can easily search for them with Google. Also at the Health, Safety, and Environment Office website, they have a searchable database of MSDSs. Hard for some of you to believe, but there is information available that is not on the internet in the form of books, and these are in the Eisenhower Library. There's a large number of these, but I've just listed the titles of 4 that I find particularly useful. These have good practical advice on the realistic hazards for a wide variety of chemicals and how to work with those chemicals safely. So if you're working with something new, it would be well worth your time to take a short walk over to the library, look up these books, and look at what they have to say about the chemicals that you intend to work with. That being said, there is good information available on the internet as well. There are databases. One that I'll particularly point out is run by the National Institute of Health. It's called ToxNet, and again, you can find a wide range of useful information about many substances in that database. For sort of quick and dirty information about hazards with chemicals in the lab, there's this thing called the NFPA Hazard Diamond, which identifies in a graphical way the hazards associated with particular chemicals, particularly things that are commercial chemicals. The diamond is broken up into 4 quadrants. The left-hand quadrant in blue identifies health risks. The top quadrant in red identifies fire or flammability hazards. And the right-hand quadrant in yellow identifies reactivity hazards. And in each hazard, each quadrant, each hazard gets rated from 0 to 4, 0 being not very dangerous and 4 being very dangerous. And so at a glance, you can look at a container for something like ethanol or acetone and know roughly what the degree of hazard is that you're talking about. A 4 in any one of these triangles represents something that you should really be quite concerned about. The last quadrant is reserved for specific kinds of hazards. So are things oxidizers, are they acids, are they water sensitive, are they radioactive, and so on. So if we want to identify the risks associated with any particular chemicals, we obviously first need to start out with knowing which chemicals are going to be used and how they're going to be used, what form they'll be used in. We'll consult the sources of information that I mentioned. We evaluate the type of hazard, the type of toxicity associated with those chemicals. We'll have more to say about this in a second. We consider the possible routes of exposure. Am I likely to inhale this? Am I likely to have something absorbed through the skin, or so on? Where possible, we can evaluate quantitative data on toxicity. This will give us an idea of exactly how dangerous the chemicals are that we're talking about. We'll select appropriate procedures and protective equipment to minimize our exposure to the chemicals. And lastly, something which we always need to worry about is we need to prepare for contingencies. Right? What if there's a spill? What if 2 chemicals that were not intended to be mixed become mixed? What if a beaker gets knocked over? These sorts of things. We prepare for contingencies ahead of time so that if something happens, we're ready. So the basic classes of chemical hazards involve toxicity, and this can either be in a general sense, that is, something can be poisonous or carcinogenic, or it can be localized. So for instance, an acid can be corrosive if it's spilled on the hand. Second category would be fire, explosion hazards, and the third category are reactivity hazards. In terms of toxicity, the toxic effects of a chemical are related to several things. First is whatever the inherent toxicity of the chemical is. Some chemicals are just more dangerous than others. But then sort of obviously the toxic effect is going to depend on the extent of the exposure. Right? How much were you exposed to and for how long? But also for frequency. How often are you exposed to the chemical? And some chemicals, and methanol for instance is one of these, may have very minimal effects for a small or brief exposure, but repeated exposures over many long period of time can lead to cumulative effects, cumulative toxicity, which can have seriously negative health effects. So we need to worry about all of these, dose, duration, and frequency. Finally, the effects are going to depend on the route of exposure. Right? Did you inhale it into your lungs? Did you contact your skin or eyes with the chemicals? Did you ingest it directly into your body, or was it injected directly into the bloodstream? All of these are going to affect the toxicity of the material. Something we sometimes don't pay enough attention to is that combinations of chemicals can be more dangerous than individual chemicals alone. This is something which is hard to get good information on, exactly how chemicals interact and their toxic effects, and in my mind represents one of the best reasons to try to minimize exposures to any chemicals, no matter how innocuous they might seem. We also need to worry about toxicity of reaction products. So if we're using reagents to carry out some synthesis, we need to worry about what the reaction products, including the intermediate stages, may be. And we also need to worry about any unintentional reactions. So if we accidentally mix two chemicals and they produce some new reactant, what is a new reaction product? What are the hazards associated with that product? These are all things that need to be thought about ahead of time. Toxins come in very many types, so we can have simple irritants, things that cause inflammation of the skin or the mucous tissues that may be reversible. Corrosive materials cause actual chemical burns. Allergens, of course, cause an allergic response, and we'll just note that the allergic response, the reaction can be delayed by hours or even days, even though it could be severe. Asphyxiants prevent oxygen transport to the brain. There are reproductive or developmental toxins that influence the reproductive organs or developing fetuses or embryos. Carcinogens, of course, tend to cause cancer. Neurotoxins affect the brain, and then even going beyond that, there are toxins that affect other organs, so the livers or the kidney, for instance. In terms of quantification, the thing you see most commonly is this thing called the LD50. This is the amount of chemical that will kill 50% of animals exposed to that chemical, and it's expressed as an amount of chemical in mass per unit mass of body weight. So in milligrams per kilogram, for instance. Sometimes the LD50 is not so convenient, so we use what's called the LC50. This is for things that are gaseous or in vapor form, and that's the concentration of chemical in the air that will kill 50% of the exposed animals. And that's expressed in ppm or milligrams per cubic meter. It's important to notice, though, that these numbers, the LD50 and the LC50, represent only mean values. The actual dose required to kill any individual could be much lower than that, so that limits their utility. And also, these numbers are not very useful for quantifying local effects, so for instance, burns from corrosive chemicals. So the LD50 and the LC50 give you some general idea about how toxic the chemicals you're working with are, but these two factors limit the utility of these numbers somewhat. The second category of hazard would be flammable hazards. Let's start by pointing out that fire requires three things. It requires an oxidizer. Usually this is air, but it's not always. For instance, in Tim Weiss's lab, they make reactive nanomaterials in which the oxidizing component is a metal that's part of the material itself, and those things can burn even in the absence of air. But usually it's air as the oxidizer. We have a fuel, which in this context we'll think of as a concentration of flammable gas or vapor in the atmosphere, and then some source of ignition. So we can control the flammability hazard by preventing the coexistence of the flammable vapors with an ignition source, and that's usually the way flammability hazards are controlled. Let's also talk about how to quantify flammability hazards. The flash point is a temperature. It's the lowest temperature at which the vapor pressure above a liquid is sufficient to produce an ignitable mixture with air. And this, it's important to note, can be below room temperature for many common materials, including acetone, which has a flash point of around 4 degrees Fahrenheit or minus 18 Celsius. So an open beaker of acetone sitting there on the lab bench generates a vapor above it, which is ignitable, which will burn if there's an ignition source. The ignition temperature is the lowest temperature at which you can initiate a self-sustained combustion reaction. And then the limits of flammability, what are called lower explosive limit and the upper explosive limit, define a range of concentrations in air that can cause an explosion. Below the lower limit, there's not enough fuel, enough of the vapor present to support an explosion. Above the upper limit, there's not enough oxygen anymore to sustain an explosion. Speaking of explosions, they're a special kind of combustion in which you evolve rapidly a large amount of gas, which creates a pressure or a shock wave. In terms of things that we deal with, organic peroxides are especially things to be looked out for because they're especially shock sensitive. And we should note that some chemicals can produce peroxides, explosive peroxides, simply upon aging. And so this is another good reason to periodically inventory the chemicals in your lab and get rid of things that are aging or not being used. Other oxidizing agents can react violently when they come into contact with reducing materials. So for instance, perchloric acid with organic compounds. Finally, let me point out that dusts can also represent an explosion hazard. So for instance, a powdered metal, if it's produced as a cloud of dust in the air, can actually produce a very violent explosion. So we need to worry about that as well. Last category of hazards are reactive hazards. So there are chemicals that react with water, there are chemicals that react with air, we call those pyrophorics. And then more broadly, there are a whole host of chemicals that are incompatible with each other and will react violently if brought into contact. This is a much too broad category to try to go into any detail here. I will just point out that there are many sources of information regarding incompatible chemicals, including the resources that I mentioned earlier in the talk. You can also get advice from the Department of Health, Safety, and Environment about incompatible chemicals. So it's a very good idea for every lab to know what materials, what chemicals are in their lab, and the other kinds of chemicals those things may be incompatible with, so that you can ensure that they don't come in contact with each other. In particular, incompatible chemicals should never be stored together. Speaking of storage, let's now talk about how we manage chemicals in our lab. And first, and maybe foremost, the idea that we can often minimize hazards simply by reducing the amount of material that we use. So we can minimize chemical orders, we minimize the amount of material that we store. We carry out our work only on the scale that we need to. And whenever possible, we substitute less hazardous chemicals if it's practical for the thing that we have in mind. All of these things go a long way to minimizing the hazards without even worrying about procedures for dealing with chemicals or personal equipment, personal protective equipment, or things that might go wrong. Chemicals that we have in our lab, of course, are stored in containers, and those containers need to be labeled. The original containers always or almost always have labels that come from the manufacturer, which are mostly adequate. They'll include the name of the chemical, they'll include an appropriate hazard warning, the name and address of the manufacturer. The thing that we need to add, which is important, is the date that the chemical was received and the date that the container was opened. These are important for allowing us to maintain some sort of control over the inventory of chemicals that we have, getting rid of things that are old, that are aging, that are no longer being used, or things that have been open too long and may have been compromised by exposure to the atmosphere. So the date, when you get a container, you should date it for the date that it was received, and when you open it, you should date it with the opening date, and that information should also go on the label. Of course, we rarely use chemicals in the containers that they are supplied with by the manufacturer. We always transfer things into temporary containers, flasks and beakers and so on. Those temporary containers also need to be labeled, and something that's particularly important and is particularly easy to fall down on is that they need to be labeled with the name of the substance in English, written out as words, not just as an abbreviation or a chemical formula. And this is a little bit of a hassle, it's a little bit of a pain, but it's important because although you may understand the cryptic abbreviation that you write on your beaker or your flask, or you and the members of your lab may understand the chemical formula, the people that come into your lab do not necessarily understand those things. And in particular, an example would be a firefighter who comes into your lab to look for hazards, for instance, if there's a fire in the room next door or if there's a fire in the room above. And that firefighter, he or she, is going to look at the things around. They'll understand what methanol or ethanol or those sorts of things are, or they'll be able to look up what kind of information on chemicals that are spelled out, whose labels are spelled out in English. But some cryptic abbreviation or chemical formula, they're going to have no clue. And although this may seem like a remote possibility, it is important that things be labeled in English. It's also important because students and postdocs, when they leave, tend to leave chemicals behind secondary containers. And it's not always possible to identify what the contents of the container are. Clearly, if it's unlabeled entirely, which is a real problem, but also if it's labeled with some abbreviation, which maybe you understand, but maybe somebody else wouldn't. So we really have to work on labeling containers properly in English. And in that regard, I took a trip through the department labs not that long ago, just looking for examples of how people were labeling things. And I came across some examples, some of which are good and some of which are not so great. I'm not going to mention any names to avoid embarrassing any students or PIs. But just as an example, I found this flask in a laboratory. It has a label on it, which is good. The label says DI plus 0.1% and then something, TFA, I think is what this abbreviation is. I'm sure this abbreviation means a lot to the person that wrote it. DI, even as a metallurgist, I can probably guess that DI means deionized water. I have no idea what TFA is. And frankly, a firefighter or someone else, a health safety person coming into the lab, probably also would not know what TFA is. So this label helps you as an individual, maybe even helps the members of your lab, but it doesn't help people that come into your lab that are not familiar with the specifics of what you're doing. So unfortunately, this label, although it's convenient, really is inadequate. Same thing could be said of this bottle, which I found in another hood. This person is at least trying. There's this abbreviation TBS. Again, I don't know what that means, and it's unlikely that a firefighter would know what that means. This one is dated, which is good. It looks like there's a date, 5/11. Doesn't tell us which year, which maybe doesn't seem important when you write it, but once things have been sitting around for a few months, it does become important. And FH, I'm going to guess, is the initials of the person that wrote the label. So this person is at least trying, which is good. This needs to be written out in English. The date should have a year, and you should write out at least your last name so that people know, who it is that created that particular container. Similar things could be said here. So these are written out in English, which is good. This says gold plating solution used. This says used copper solution. The problem is, of course, that the individual components of this have not been identified. Right? Presumably water is part of it, but maybe alcohol or something else and some other chemicals. The chemicals need to be labeled or spelled out on the containers. And again, they need to be spelled out in English, right? So over here, we have H2SO4 in water, which is sulfuric acid. But a firefighter or someone else walking in the lab isn't necessarily going to know that. So this needs to be written out in English. Here's an example of something which is a little bit better. So in this case, the name of the chemical is written out, so everybody can see that this is acetone. This one looks unlabeled, but I can tell you there's actually a label on the back side of this squeeze bottle. One thing I'll point out is that you can buy squeeze bottles which come pre-labeled, which can be convenient for things that you use often in your lab, for isopropanol in this case, or also ethanol and acetone and things like that. So if you get weary of writing out these labels all the time, these pre-printed bottles are also available. Let me hold this up as a quote best practice for how to label chemicals. This is what we do in my lab. And the thing that I like about this is that it ends up being actually pretty easy, because what we do is we print out labels like this. This has been increased in size, but these are just printed onto label sheets, which you can buy at any office supply store. And they're pre-printed with a space for the chemical name, the hazard, the basic hazard, the name of the person that created the secondary, the temporary container, and the date at which they did so, and then also with my name and our contact information. And when these are pre-printed, we pre-print them, dozens of sheets at a time, so there are hundreds of these in the lab, and then it's easy to just take one out, fill in the information, stick it on the secondary container, and the whole thing takes about 30 seconds to actually do. So if you're having trouble labeling things, doing something like this, a few minutes of effort ahead of time will make it pretty easy to do this in the laboratory. In terms of transporting hazardous chemicals, the key thing is to make sure that we're using secondary containment. So a good example of this is this 4-liter bottle, which is in this rubberized container. The key, of course, for secondary containment is that it protects the primary container, but also if the primary container should break, the secondary container will contain the chemical and prevent an actual spill. What goes along with that is that on these sorts of containers, we don't carry them only by the neck ring, particularly if they're full. So one hand on the neck ring if you're only carrying the bottle, and then one hand underneath. If you have any large quantity, and I would start to call a large quantity anything more than about one of these bottles, those should really be transported on a cart. It just gives you better control over what's going on. When you're transporting, please plan your route such that you minimize the exposure to the general public in the event that there should be a spill. So for instance, if you're bringing chemicals down from Mudd Hall, coming down the stairway between the upper and lower quads is probably not the best idea, because there's a lot of traffic, foot traffic, that gets funneled right through that spot, and lots of people would potentially be exposed if you were to spill a chemical in that particular place. Along the same lines, if you're using an elevator with any sort of hazardous chemical, don't allow other passengers at the same time that you're transporting the chemical. Chemicals need to be stored appropriately. There's a couple of key things here. Flammable chemicals in containers larger than 1 gallon must be stored in a flammables cabinet. Right? That's by Hopkins policy and by law. I would go so far as to say that even 1 gallon of a flammable chemical is quite a bit. In my own lab, we store containers of that size in our flammables cabinet, only bringing them out when we actually need them. We don't mix different types of chemicals in the same cabinet. So for instance, we don't store acids and bases in a flammables cabinet, and we segregate acids from bases. More generally, we don't store incompatible chemicals together. And again, for the chemicals that are in your lab, you should seek out sources of information about what kinds of chemicals are incompatible and make sure that they are not stored together. In the event that some chemical does get spilled, we want to have enough material on hand to deal with that spill, so enough absorbent or neutralizer, so that even a serious spill of a large amount of material in our lab we could handle and contain and absorb. So these things may seem sort of obvious, but this is what a flammable storage cabinet looks like. This happens to be the one in my lab. They come in different shapes, but they're always labeled. Notice in this lab there's one storage cabinet for acids, there's another storage cabinet for flammable materials. This is a nice example that I'll point out from Michael Yu's lab. They have a separate metal cabinet in their lab on the lab bench, which is labeled chemical spill cabinet, and in here are the absorbents and neutralizers they would need in order to deal with any chemical spill in their lab. And this is nice because it's out, it's prominent, everybody can see it, and so everyone knows where to go immediately to find materials to contain a chemical spill. I have to say in my own lab we have absorbents and neutralizers and things, but they're not necessarily so obviously displayed, and so it would probably take us a little bit of rooting around to actually find them in the event of a spill. Okay, now let's talk about how to work with chemicals safely. Fundamental principles are things that we've already talked about. First of all, plan ahead. Right? A little forethought goes a long way into minimizing the opportunity for things to go wrong and for there to be safety problems. As a general rule, we try to minimize exposure to any chemicals, particularly things that are hazardous. Don't underestimate the risks. This is not so much a problem when you're working with something which is hazardous for the first time. Although it can. I mean, some people can blithely go into an experiment without having any idea of the risks of the hazards of the things that they're working with. But what's particularly insidious are the risks that come about when things become routine. When you've done the same process or a similar process or procedure on a particular chemical or group of chemicals many times, as things become routine, they become familiar, and the risks somehow become more distant. This is true. I mean, the classic case is driving, which is something that we all do, or many of us do, every day, which is certainly has risks associated with it, but those risks are usually not forefront in our minds, just because the procedure has become so familiar to us. So in particular, when you find yourself doing routine things, taking an extra second to just think about the risks goes a long way. We want to be prepared for accidents, right? You want to think ahead of time about what you will do if there's an accident, what kind of accidents are possible, and what the proper response would be. Having things, for instance, on hand to deal with chemical spills would be part of this. And this probably goes without saying, but proper personal behavior everywhere in the lab is important. No jokes, no horseplay. It's not a place for messing around. Let's talk specifically now about how to avoid particular kinds of injuries. We worry a lot about the eyes, both because they are particularly vulnerable but particularly valuable to us. And the golden rule here is that eye protection is required at all times in all labs, right? Even if you're not performing a chemical operation. And the reason for that is that even if you're not performing a chemical operation, somebody else may be. Somebody else may be performing a chemical operation and then have some trouble and call to you and ask for help, if there's a spill or something like that. So even if you're not performing a chemical operation, you must be wearing eye protection at all times in all labs, right? And this is a rule for all labs in our department. A corollary to this is that if you see someone else not wearing appropriate eye protection, that you should remind them about the importance of that and ask them to put eye protection on. For routine use, safety glasses are okay. They provide protection against lots of hazards. If you're working with particularly bad chemicals or things under high pressure or vacuum, goggles are better. They provide better splash protection and better impact protection. Full face shields are recommended if you're working with particularly hazardous things. And in my group, I go so far as to say, if we're working with, say, for instance, large bottles, like the 1-gallon bottles of concentrated acids, that's a sufficiently hazardous operation that we prefer to wear actual face shields. The time involved in putting a face shield on is minimal compared to the protection that it actually provides you. And again, it always pays to remind ourselves about the use of protective equipment. So this is from Jonah Erlebacher's lab. Someone there is a pretty good artist, and it's a humorous but useful reminder about eye protection. Inhalation is another potential route of exposure. So things that involve things that we can, procedures that involve things that we could inhale. So for instance, vapors or dusts, those things are done in fume hood. In the fume hood, you have to use it right, like any piece of equipment, in order for it to protect you. So any materials in the fume hood should be kept at least 6 inches back from the sash. The sash should be kept in the lowest possible position, right? Even when you're working in the fume hood. This position is usually inconveniently low, but it is important to be kept low, such that the fume hood continues to draw effectively and that you get the best possible protection from any splashes that might occur in the fume hood. Something that many of us tend to lapse into is allowing things to clutter up our fume hoods. We shouldn't allow them to be cluttered with bottles or equipment for a couple of reasons. One is if the fume hood is too cluttered, then the fume hood may no longer draw effectively. The other reason is that things that are in the fume hood can become part of the accident. So for instance, in the case of the researcher from UCLA that I mentioned at the beginning, hexane was in an open container in her fume hood, even though it wasn't part of her experiment, and it contributed to the accident that she had and made it worse. So this is another reason to not allow your hood to become cluttered with excess stuff. So I ran around taking a few pictures of fume hoods in the department as well. This is one in my lab. Just to point out that nobody was using the fume hood at the time that I took this picture, but notice the sash is in a pretty low position. Notice the fume hood, by and large, is not very cluttered. There's a little bit more stuff in here than I would really like. Maybe a third to a half of the black baffle at the bottom is actually blocked. But overall, it's not too bad. One thing that I'll point out that I didn't mention earlier in terms of storage is that notice that these bottles are in secondary containers, these basins. So even if one of these bottles should leak, the secondary container would contain that spill and prevent it from becoming uncontrolled. And so we do this not only in our fume hoods, but also in our storage cabinets. So if there's a leak in one of our bottles in the storage cabinets, the same principle of secondary containment applies. And this is a good practice that I think really everyone should apply. Another thing that I'll point out, which we'll get to in a few minutes, is this thing right here is a tube of calcium gluconate gel, which is the antidote for exposure to hydrofluoric acid. And that's out where everyone can see it and use it should the need arise. Here's another fume hood from a group that will remain nameless. This fume hood is a little bit more cluttered. Notice that these containers, there's some containers over here in secondary containment, but these bottles are not. These bottles occupy almost the entire back wall of this particular fume hood. Notice that at least one jar here appears to be unlabeled, right? So all of these things are problems. Similar thing could be mentioned about this fume hood. Again, it's pretty cluttered. There's a lot of stuff in here which is apparently not really being used. Again, almost the entire back baffle is blocked, either with this tub or with all of these bottles. Notice this fume hood, just in the position that I found it when I walked into the lab, was nearly completely open, and this little piece of tape or fabric here, which is intended to indicate whether or not the fume hood is drawing, was just sort of hanging limp. So if there's anything noxious in here, which is releasing vapors that you would not want to be exposed to, it's not being drawn off out of the fume hood. It's just sort of mixing around and coming out into the environment. And this fume hood in this situation is basically not doing anybody any good at all. We also worry about skin contact. So we minimize skin contact by wearing gloves that are known to be impermeable to the substances, the chemicals that we're dealing with. And in that regard, I'll just point out that there are many different kinds of gloves, and there are many, many different kinds of chemicals. Not all gloves are good or compatible with all chemicals. So you can find charts like this, this glove compatibility chart. I just downloaded this one from the VWR website. Across the top, it lists a variety of different kinds of gloves, and then on the left-hand side are a bunch of different chemicals. And so you can find out, for instance, that ethanol, with this what's called the Silver Shield glove, every box here is green, which indicates good for total immersion. That is, you could, your hand in the glove could be immersed in ethanol, and it would provide protection from ethanol, nearly indefinitely. Things that are yellow are good for accidental splash protection or intermittent contact, which is usually mostly what we worry about. We don't usually worry so much about total immersion. But the things to watch out for are the ones that are in red, right? Those represent situations or combinations of gloves and chemicals that will fail even with a short exposure to the chemical. And in some cases, having the glove on can actually be worse than not having a glove at all. So for instance, latex gloves are permeable to many organic solvents. If you wear a latex glove and you get an organic solvent on it, the solvent can go right through the glove. It's because the glove is permeable, and the solvent will then be trapped against your skin because the presence of the glove will slow down the evaporation of that solvent. So you can actually increase your exposure to chemicals by wearing the wrong gloves. So having a glove compatibility chart or looking up a glove compatibility chart like this is really important, so that you know that the gloves that you're working with are appropriate for protection against the kinds of chemicals that you're working with. And in particular, anytime you start dealing with a new chemical, consulting a chart like this is really, really important. If necessary, if your gloves have become contaminated, then you should, of course, wash them before you remove them. And if gloves have been contaminated or are potentially contaminated, you should really remove them before you touch other things like doorknobs or telephones or computers. This is to prevent transfer of those chemicals from these items to someone else that may be, or yourself, if you're using those same items when not wearing gloves. Along the same lines, I would say that wearing gloves that are potentially contaminated outside the laboratory is really not a good idea. And doing things like walking up to the copy room or down to your office wearing gloves the whole time really should be discouraged. If you're out of the lab for any significant amount of time, take the gloves off, dispose of them properly, and put on a new pair when you go back into the lab. We don't want to spread chemicals all over the department. Speaking about clothing and protective apparel more broadly, any loose hair or long hair or loose clothing or jewelry should be confined, a barrette or a ponytail or something like that. One thing that is perennially an issue is that students like to wear sandals or open-toed shoes in the lab, and these are just not permitted. They don't provide protection against anything which is dropped on your foot, or if a glass bottle of a chemical is dropped on the floor and splashed. Open-toed shoes obviously don't give you any protection. So closed-toed shoes are what you wear in the lab, and if possible they should be made out of leather, because leather provides the best protection. Things that are synthetic can be permeable to chemicals, particularly if they're sort of porous or mesh like many synthetic shoes are. So leather closed-toed shoes really are the best choice for the lab. We strongly recommend that you wear a lab coat when working with chemicals, particularly if your clothing leaves any skin exposed, and lab coats are required if there's any skin exposed above the knee. So if you're wearing short sleeves or if you're wearing shorts, which we discourage, put a lab coat on top to protect, to cover any exposed skin above the knee. As I mentioned earlier in the case of the researcher from UCLA, if she had been wearing a lab coat over her synthetic sweater, she probably wouldn't have died from her burns. Lab aprons provide even greater protection if you're working with some hazardous substances. So again, to go back to the issue of large amounts of concentrated acids in my group, I ask my students to wear a lab apron so that if in the worst case scenario that a large bottle breaks and a significant quantity of acid should spill on them, that they would be protected. And along the same lines, synthetic fabrics are inadvisable, right? They tend to dissolve in contact with certain chemicals. and they also tend to be more flammable. Cotton, of course, is flammable, but not as flammable as many synthetics, and so cotton is generally preferred. In terms of housekeeping, it's important that we don't block access to exits or emergency equipment. If there is any incident that involves or requires evacuating the lab, we want to be able to do that quickly. We don't want to have stuff stacked in front of the showers, the eye washes, for instance, that would prevent access to them. Even relatively minor hindrances may become significant. It's one thing if you're in the lab and you have a spill in your eyes or splash in your eyes, and someone's there to help you to the eye wash. But if you have to try to find your own way to the eye wash with stuff blocking your way, that becomes another issue entirely. We want to keep our work areas clean. We want to clean them regularly, including the floors. The reason for this is that we don't want any chemicals that may be around to accumulate on surfaces, including lab benches and floors and things like that. If you ask, housekeeping is not very good about this, about doing it regularly, but if you ask Marge Weaver, she will get housekeeping to come clean the floors in your lab, and I recommend that you do that on a regular basis. In terms of physical hazards, this is the topic of a separate video, but I thought I'd mention it here. Compressed gas cylinders have the potential to become torpedoes if the gas is released in an uncontrolled manner, so compressed gas cylinders must be secured to a wall or other immovable object. We don't store chemicals on the floor. That's just asking for trouble for them to be kicked or run into with a cart or something like that. And we don't use hallways as storage areas for same reasons. If a chemical spill should happen, the thing to do is to evaluate the spill. Right? And this you can do relatively quickly. There are three simple and maybe obvious questions. Are the materials hazardous? How much of material has been spilled? And those two things together will give you some idea of the danger to people and property. And these things will tell you whether or not the spill is something you can deal with on your own or whether or not you need to get help. If it's something that you can deal with, if you can contain the spill, do so. This could be with the absorbent materials we talked about earlier, the neutralizers, or if appropriate, something as simple as paper towels. If you can't deal with a spill, then you can evacuate the area and call for help. And we'll talk a little bit later about where to call. You can call a security number or 911. You can also call Health, Safety, and Environment for dealing with chemical spills. If you can clean up the spill yourself using the techniques and the materials that you have at hand, you can do that. Health, Safety, and Environment can also be called in to help with cleaning up and decontaminating areas. And just a reminder that if you do neutralize or absorb hazardous materials, that contaminated material that results is probably hazardous material as well and needs to be disposed of as a hazardous material like you would with other excess chemicals. If you or someone else is actually exposed to a chemical, say on the skin, it's important to take immediate treatment steps as quickly as possible. If the spill is on the skin in a relatively small area, you can flush that area with water. The key thing here is to flush it for a long time. 15 minutes seems like a very long time, but it's important that you remove all the contaminating material as thoroughly as possible. If what's happened is not a burn, a chemical burn, you can wash the area with warm soap and water, and that will also help to remove the contaminant. You should check the MSDS for possible delayed effects, and you should seek medical attention for particularly hazardous materials or for things, even for minor chemical burns. An exception to all of these is how we deal with hydrofluoric acid. Hydrofluoric acid is particularly nasty because it doesn't burn so much as it gets absorbed into the skin, where it can affect the nervous system and it can attack the bones. And a relatively small amount of hydrofluoric acid can actually be lethal. The treatment for hydrofluoric acid is different. What we want to do is we want to treat with calcium gluconate gel, which is an antidote. It reacts with the hydrofluoric acid and prevents it from being absorbed into the body. So the treatment for a hydrofluoric acid spill is to rub calcium gluconate gel onto the area of affected skin to absorb the hydrofluoric acid and then to seek medical attention. It's for this reason that if in your lab you work with hydrofluoric acid, you should really have a tube of calcium gluconate gel handy. And I'll also point out that the expiration date or the lifetime of calcium gluconate gel is pretty short. It's on the order of a year. So you should regularly check your calcium gluconate gel to make sure that it's not exposed. This is one of those areas where a little forethought goes a long way towards preventing some potentially serious effects. If there's a larger spill, for instance on your clothes, one thing to do is to not attempt to wipe the spill away. Right? In that case, you spread the risk of simply spreading the material around. The thing to do is to quickly remove any contaminated clothing, go to the safety shower, and use the safety shower to wash yourself off again for at least 15 minutes. When you're removing the contaminated clothing, take care not to spread the chemical around. Particularly, don't get it into your eyes. Any large spill like this requires medical attention, and any contaminated clothes should be discarded of, or maybe if it wasn't a corrosive that actually damaged the clothes, they could be salvaged by being washed. But they should be washed separately from other clothes to prevent spreading the contamination around. In case you don't know, this is what a safety shower actually looks like. This is over in Krieger Hall. Here's the top of the shower where the water comes out. Here's the thing that you would actually pull to get the water to come out. And this is a combined safety shower and eye wash. So here's the eye wash as well. You should know where the safety shower is for your lab, and you should make sure that access to it is not blocked by equipment or other things being stored in front of it. If you get any splash into the eyes are particularly vulnerable to damage. So you immediately want to flush with water for at least 15 minutes using an eye wash. So here's one of the eye washes in my lab, in addition to the combination safety shower eye wash, which I showed you a second ago. I'll just point out that this eye wash is on a hose, so you can actually pull this thing out and hold it right up to your face and run water to both eyes simultaneously. One thing which is not obvious when dealing with an eye wash is that it's possible to get chemicals behind your eyelid where the eye wash won't effectively flush them out. So it's important to hold the eyelids away from the eyeballs and move your eyes around to thoroughly wash out the entire eye. And in this regard, it's very helpful if there's someone there with you who can either do the part about holding your eyelids or can do the part where they actually hold the eye wash so that you can manipulate your eyelids. And any chemical in the eye should be cause for seeking prompt medical attention. Finally, let's talk about working with flammable chemicals. So we want to handle flammable substances only in areas that are free of ignition sources. So there are no open flames. Electrical equipment can create sparks, especially electric motors, or static electricity. All of these are things that can ignite flammable materials. Corollary to this is that we never heat flammable substances with an open flame. We do something like a hot plate or an immersion heater or something like that. And finally, we want to ventilate. A key is to ventilate to dilute the vapors to the point where they are no longer flammable. So we typically work with flammable materials in a fume hood, which provides the ventilation to make sure that we stay below the flammable limit of the vapor. Okay, finally, let's talk about disposal of chemical waste. And maybe the first thing to say here is that at Hopkins, we don't call it chemical waste or hazardous waste. Calling it hazardous waste creates a legal conundrum for us, where if you're collecting hazardous waste in your lab, that makes you a hazardous waste generator, which puts legal restrictions on you. So instead, what we refer to as the collection and disposal of excess or unwanted or used chemicals, and we leave the hazardous waste designation up to the health and safety professionals. So how we deal with excess hazardous chemicals? We collect them for disposal in a container made of the same material as the original. So how do we dispose of excess hazardous chemicals? We collect them for disposal in a container made of the same material as the original, preferably in the same container that the original came in, if that's possible, or the same chemical anyhow. We can use other containers as long as they are compatible material. And we should always wash out containers. It's recommended you actually wash out a container 3 times, rinse 3 times, and then dry before you use it as a container for collecting hazardous waste. Notice that you need to label each container, particularly if you change the contents, as we'll talk about in a second. So the contents of all containers must be clearly identified with a label that gives the chemical name. Again, it has to be in English, not just in some abbreviation or chemical formula. And if it's a mixture, you need to list the components and the approximate percentages. Approximate percentages are fine. If it's roughly a 50-50 mixture of acetone and ethanol, and that's what you put on the label, nobody is going to come back to you later and say, hey, it was actually 60-40 mixture. Nobody cares. We just want the approximate percentages so we know what is in each container and roughly how much. Also, the label needs to have the contact information in terms of the name of the principal investigator or the research advisor, the location of the lab, building and room number, and a contact phone number. Hopkins provides these pre-printed labels which we can use. On the one side is a list of the chemicals that go in, the chemical names. Again, it's no formulas or abbreviations, and the approximate percentages. And on the other hand, other side are contact information: name, phone number, building, and room number. To dispose of those chemicals, we need to transport them to Macaulay Hall, to the basement. There are 2 times on Thursdays each week where hazardous chemicals are collected, 10:30 to 11:30 in the morning and 1 to 2 in the afternoon. Please use secondary containment when transporting chemicals, so those rubber buckets as we illustrated earlier. And if possible, use a cart, certainly if you're carrying any significant amount of material. And again, choose a path that will minimize exposure to the public if there is any accident or spill. And finally, if you get to Macaulay Hall and you don't find anyone there, don't leave your waste unattended there. Wait until someone comes so that you can turn it over properly. That pretty much concludes this presentation. Let me just summarize with a few key points. Let me reiterate that you ultimately are responsible for your own safety. So the things that you learned in this video and in the training that takes place in your lab, you have to accept responsibility for implementing for yourself. No one can be there with you at all times, making sure that you're doing things safely. You have to decide that you're going to do it. Second thing is to make sure you plan your experiments. Think ahead before you do something. A little forethought goes a long way in terms of minimizing your risk and the chances that there will be an accident, or if there is an accident, it will maximize your ability to do something effective about it to make sure that no one is hurt. What goes along with that is that you should get in the habit of evaluating risks and hazards all the time when you're in the lab. You should be looking around, looking at things and thinking about the potential risks and hazards that are there. If you see unlabeled containers, if you see too much stuff in the fume hood, if you see someone not wearing a lab coat or not wearing protective eye equipment, these are all hazards or risks, and we should be thinking about them all the time. The things that you work with, you should be intimately familiar with. So know the properties of the chemicals and the procedures that you're working with, and follow those proper procedures for working with chemicals and for disposing with them, including the appropriate personal protective equipment. So things like gloves, eye protection, lab coats, and so on. If you do these things, these will go a long way to making sure that your work is done safely and that no one is injured, yourself, your lab mates, or anyone else. And to finally reemphasize that to all of us in the department is the most important thing, that our work is done safely and that no one gets hurt. Let me just conclude by saying that if you have any questions about any of the material in this presentation or the work that's done in your lab, you should feel free, and you should actually, I strongly urge you to ask questions. You can ask questions of your PI or the other members of your lab group. You can also ask questions of me as the chair of the safety committee in the department. You can also ask questions of the people of health, safety, and environment. If you don't know something, please ask. It's much better to do that than to have an accident. With that, I thank you for your attention.